Um, Anyways, we will wait till 7:05 and see if anyone else is joining. Then we'll start. So my name is Annette. I am the TA, one of the TA for this course. So I am a PhD scholar in IIT Tirupati. Um, yeah. Are you guys here? Can anyone respond? Am I audible? Yeah, thanks. Yeah, if you don't want to speak, like open your video or audio, then it's fine that you can chat in the chat box. It's fine. So since we are like a very small group, we can have an interactive session. Like I can ask you questions, and if you are comfortable, you're not comfortable with talking to me directly, you can always put it in the chat box. And if you have any doubts, you can stop me at any time and you can ask. Um, Good evening. Good evening to all. Thank you for joining. Yeah, this session is like an interactive session. Like we can discuss the doubts. But this week I'll be taking, going through the week 0 assignments of the past year course. And I think the same questions were given this year also. So we can just go through it and have a look. And next week I'll be solving the week 1 assignment. I just checked the week 1 assignments last date is tomorrow, so I can't discuss it today, but next week we can discuss that, and if you have any other doubts in the course, that also we can discuss. This is like a doubt session, not a summary session, but if you guys want a summary, maybe next week I can try that as well. Okay, maybe one more minute. We'll wait till 7:05 and then we'll start. So all of you are undergraduate level or MSc or anyone who is working. Guys, you should interact with me. It is We are just a small group. We are only 7 plus 1 8. Yeah, okay. Undergraduate. um okay. UG first year. What about others? Okay, PG. Okay, good. Okay, I think now we will start. So if you guys have, okay, that's fine. Yeah. So this is, as you know, this is like an undergraduate level course. So everything will be in an introductory format. So if you guys have any doubts, even if you think it's like very silly or not up to the level, that doesn't matter. We can always discuss that. That's why we have these live sessions, right? So we'll start. One second, let me share my screen. Is the screen visible to all? Okay. So as we all know, we are here to discuss the doubts in the basics in inorganic chemistry. So if you guys like at any point, if I am not audible or if you have any issues, please open your mic and tell me, because sometimes I won't be looking at the chat box. But like at the end of each question, I look at the chat box. But if you have anything in between, please tell me directly. So my name is Annette. I am a PhD student in the Department of Chemistry at IIT Tirupati, and this is my email ID that you can contact me at any time to if you have any doubts. Okay, so the assignment zero is like just to give you an idea, like what all things that comes under the title of inorganic chemistry. So if you have seen the assignment questions, you would have seen like different topics and different questions. So I'll just go through all and like we'll try to solve. And if you have any, one second, someone is joining. Okay, people are joining. One second. Okay, so my screen is still visible, right? Okay. So we'll just go through the questions. So this is the first question. Um, what will be the nomenclature of element of atomic number 108? So, for most of the elements, we know the names, but for the elements which are above 100, that for that those elements, IUPAC, or IUPAC is the International Union for Pure and Applied Chemistry, they have given a set of rules to name the elements above 100, because this was put forward because at that time when the rules were proposed, the elements were not discovered. So to instead of just leaving the blank space in the periodic table, they just proposed that okay, maybe we can just just give a name, systematic naming, and when the elements are actually found, we can just replace those names. So so that is what comes under this nomenclature of element of atomic number 108. To help you answer this, so I have given this digits and their corresponding roots and the abbreviation. For example, if the digit is 0, then the root word for that 0 is nil, and if the digit is 1, the root word for that digit is un. Like that, we have bi, tri, quad, pent, hex, sept, oct, n, etc. And for each root word, we have a corresponding abbreviation like N, U, B, T, Q, and so on. So I'll just solve one example, and the actual question we'll solve together. Okay. So let's say, for example, what will be the one second. What will be the name for one second. What will be the name for this element 118? So for 1, you have to look at the root un, so it will be un. Then again there is another one, so again un. For 8, the root word is oct, so it will be oct. And all these will end in a suffix called ium. ium. So another example, let's say 115, again it will be un. Then for 5 we have pent, so pent. Then we have the IUM, so it will be pentium, right? So now I think you will be able to solve this question 108. What will be the answer? I'll give you 1 minute. I'll look into the chat box. You can put it in the chat box. 108. Okay, 108. Good. Most of you have written the right answer. Let's discuss anyways. So the question is 108. So the root, 1 second. So the 108 is the question. So the first root will be un, then the second is 0. So zero's root is nil. So un nil, then 8 is oct. So oct, then un nil octium. So now I'll give you, so whoever wrote this answer is right. So the right answer is option A, un nil octium. So now I'll give you a reverse exercise. What will be the atomic number of this option D? What will be the atomic number of this element? You can write it in the chat box. Okay. Okay. So yeah, everyone have answered it right. So it is first root word is um, first root word is un, so which is like 1, and second is also un, so it is also 1, so the third is also 1, so it is 111, right? So if do you guys have any doubts in this slide? Okay, okay, good. So this is just a, I just wanted to show you guys, now even though we have this IUPAC nomenclature for the elements after 100, all the elements are now discovered and detected. So now all these elements have renamed into their IUPAC official name, like all these names. These names are, normally discussed upon by the whoever discovered this element as well as the IUPAC. They'll have a discussion together and they'll decide which name they'll give. So sometimes it is the name of the place, sometimes it is the name of the lab which it's synthesized, sometimes it is the name of the scientists who were involved in the synthesis. Sometimes they just give the name to of other scientists to just give respect to them. For example, this Nobelium is named after Alfred Nobel, then Rutherfordium is named after Ernest Rutherford, and so on. And there are some example for Moscovium. Moscovium is named after a city, Moscow, which is in Russia. Then Tennessee, which is a city or state in US. Okay, people are joining. 1 second. Let me. Okay. Yeah. Hmm. The questions were different for you guys. I am not sure because I could not see the assignments zero for this week. I have just taken the assignment zero of last year's course. What? Okay. Okay, okay. But I am talking about the week zero assignment, not the week one assignment. So I am not sure if it's were the same. This is the past years. I mean, past year also this course was run. So whatever assignment that they gave last year, that's what I am discussing here. Next week I can discuss, last year's question paper assignment as well as this week's. I mean, this year's. Hmm. Okay, so you see the trend. It is like all the elements are now named, and like if you see they have kept this IUM for almost all the elements except for this tennessine and organocin, because tennessine belongs to the halogen group, and halogens, as we know, one example is fluorine, and it has this INE word. So and another example will be chlorine. So all the halogens have this, are ending in this INE. That's why they have like consider this tennessine, like INE they have added to indicate that it is a halogen element. And this organocin belongs to the noble gas family, and example for noble gas is argon. Then we have xenon. So it all ends with ON. That's why this organocin has an ON. Um, okay, you guys please give me 1 second. Okay. Okay, so do you have any doubts in these slides? Okay. Okay, so moving on to the next question. So this is a general question. What is the order of increasing energy of orbitals? So uh, normally it is like from school level we have studied the Aufbau principle. It is like a empirical rule or method to understand in what order the orbitals are arranged. So you can just uh, look at the end of the arrow to the head of the arrow, and that's how the energy changes. So 1s has the least energy, followed by 2s, then 2p, 3s, 3p, 4s, 3d, so on. And this Aufbau principle is actually based on a rule called n plus l rule. This is also an empirical rule. It does not have any experimental consequences, but this helps us to just identify what is the order. So according to this rule, whoever has the least n plus l value will have the lowest energy. And the n is the principal Corner number, the orbital angular l is the orbital angular momentum Corner number, or also known as the azimuthal Corner number, and m is the magnetic Corner number, and s is the spin angular quantum momentum. Spin angular momentum Corner numbers. I'm sorry for the typo here. So as we all know, n that varies from 1, 2, 3 to infinity, and L varies from L can have L is fixed for s orbital. It is 0 for p. It is 1 for d. It is 2 for f. It is 3, and so on. And m varies from plus L to minus L. For example, if I say 2d, the n is 2 for, and L is 2 because it is d. M is plus 2 to minus 2, including 0. So it will be plus 2, plus 1, 0, minus 1, minus 2. So there will be 5 substates. And S can be plus half or minus half. Right? So here we'll see what this n plus L rule really means. For example, we'll take the 2s. So 2 here, the for 2s, n is what? 2. S for s, L is 0. So n plus L is 2 plus 0 is equal to 2. Right? Then let me take 2p. N is equal to 2. For p, L is 1. So n plus L is 2 plus 1, 3. So uh, definitely 2s has the lowest n plus L rule. That's why it has this lower energy than 2p. But what if n plus L value is the same for both? Here we will consider the example of 3s. 3s, n is 3, s, L is 0. So n plus L is 3 plus 0 is equal to 3. And if you look at 2p and 3s, you can see that both have the same L plus N plus L rule. So in that case, you will look at the you will look at which one will have which one has the lowest N. So here 2p has the lowest N is equal to 2, 3s is N is equal to 3. So this has the lowest energy. One second, people are joining. Okay. So on the basis of N plus L rule, we can find out the ordering of these orbitals. So I think this is pretty straightforward, and I think all of you know the answer. So can you please tell me in the chat box which option is right, A, B, C, or D? Right? Anyone else? Yes, yes. So everyone have answered it rightly. Good job. So I also want to discuss some other laws, which is the Hund's rule of maximum multiplicity and the Pauli's exclusion principle, that sometimes can overtake or overbear the Aufbau principle. For example, if we consider the um, chromium, the atomic number is 24. So if I write the electronic configuration, so if anyone wants to like answer what will be the electronic configuration for chromium, not in chat box. Anyone would like to say? Okay, looks like no one is interested. So we'll just look at the Aufbau principle and go. So first definitely is 1s, then it will be 2s, 2p, 3s, 3p, 4s, 3d. So 24 electrons are there. So 1s2, 2s2, 2p6. So this is 10 electrons we have counted. Then we have 3s2. So 10 plus 2, 12. Then 3p6. So how much is this? 18. Then you have to write 4s, then 3d, because that's what we saw here, right? 3p, after 3p 4s will come, then 3d. So for this is 10 plus 2, 12, plus 6, 18, then 20, 24. This is one way of writing. And actually if you look at this block, it is 18 electron, right? So the 18 electron configuration is corresponds to argon. Argon is a noble gas. So instead of writing all these, we can just write argon in bracket, then 4s2, 3d4. Now a question comes, is this the right one, or 4s1, 3d5? Which is the right one? Yes, second one is the right one, because here, as you know, the 3d has 3, 4, 5. So this is the half filled state, and 3d 4s. So in this 4s1, 3d 5 state, both are in half filled state, and this has an extra stability. This is explained by this Hund's rule of maximum multiplicity, which states that whenever there is a possibility of having the maximum spin multiplicity, the electrons will go for that configuration. The spin multiplicity essentially means the spin multiplicity is calculated by an equation 2s plus 1, where s is sum of uh, all the spin angular momentum. So if I have 5 electrons here, each has an s of plus half, right? So I can count plus half is 1, then another plus half is 2. So basically I have like 2 5 into plus half, right? So my s value is 5 by 2 here. and this multiplicity will be 2 into 5 by 2 plus 1, so it will be 6. And if you look at the 3d4, what will be the name, what will be the 2s plus 1? Can anyone answer? Okay, let me ask, what will be the s for this 3d4 case? How many unpaired electrons are there? No, no, I am asking 3d4. So here we have 3d5 and 5 unpaired electrons are there. So S will be, the sum of the S will be what? 5 into half, because all are plus half, right? So here it is 4 electrons are there. So what will be S? What will be the sum of all these spin angular momentum? Yeah. No, no, no. Uh, yeah. That is another thing that I wanted to tell. When we like when the electrons are singly occupying, they will occupy in the in the same fashion, like all will have s is equal to plus half, or otherwise all will have s is equal to minus half. If it is mixed, that energy of that configuration will be much larger than this configuration. So, and you know that always these electrons like to be in the most stable configuration, right? So this will be the configuration, like everyone will be having plus half. So now what will be the sum? So each electron is giving, yes, so it will be 4 into half, so it will be 2. So S is 2, so 2s plus 1 for this state is 2 into 2 plus 1, which is 5. See, here it was 6, here it is 5. So the spin multiplicity is higher for this 3d5 case, which is why it is more favorable than this configuration. The same thing happens in the case of um, copper 29. Copper 29. For this case, it has argon, then 3d 10 for S1. Here it is completely filled. So as you know, completely filled is also like very much stable than like partially filled orbitals. Um, so that is the Hund's multiplicity, rule of maximum multiplicity. Then moving on to the Pauli's exclusion principle. So it is, I think all of you knows this. So this is the p orbital, and if I have say 4 electrons, how will I fill them? Simply 1, 2, 3, and the fourth electron I have to fill the opposite direction, right? 1, 2, 3, it will be like this, right? So why do we have to fill this electron in the opposite direction? That comes from this Pauli's exclusion principle. Pauli's exclusion principle states that all 4 quantum numbers cannot be the same for both electrons in the same orbital. But this all 4 cannot be the same for both electrons in the same like orbital here. But this and this can be same, but in the same orbital it cannot be the same. This actually stems from something called the anti-symmetry principle, but it is not related. It is actually out of scope for this course right now. But if any of you guys are like interested, you can email me, and if a lot of people are interested, maybe next time we can discuss it also. So if do you guys have any doubts in related to this question? Okay. Hmm. Ah, so in the case of transition metals, there is something called this low spin, high spin and all. That happens when when the transition metal is surrounded by other ligands, then how these ligands interact with the metal, that will dictate if the orbitals will be high like low spin or high spin. So I'll just show what it actually means. Let me just So the metals in the complexes, they don't have like the say the orbitals of metals are not degenerate when they participate in complexes. So for example, in a free metal we have all the d orbitals of the same energy, but when some ligands come in, some kind of interactions are happening, this this orbitals will be split into different energy levels, depending upon where this ligands are coming from. So if some ligands are coming, say like directly to the electron cloud, or if they are away from the electron cloud, based on that this energy levels will be split. So I will show the splitting pattern for octahedral complexes. Octahedral complexes means one metal is surrounded by 6 ligands. So in that case we have this splitting. So this is called uh, this level is, yeah, T2G and EG levels. So here I'll explain what is low spin and high spin. So if the split the pattern is like this, the filling is like this, then it is like a high spin complex. And if it is something like this, then it is a low spin complex. So it essentially means high spin means more unpaired electrons are there. The spin multiplicity is very high. And in low spin means the spin multiplicity is less. But here the stability, we cannot say that, okay, this is more stable, this is more stable without seeing what kind of ligands we have, and how this electrons are like electrons, do the electrons like to go here or go there, depends, also depends on the type of ligands. So that I am not going into much detail right now, but if you guys want we can discuss at the end. Hmm. Hmm. No, it generally okay, the actually this high or low, that terminology is not that much clear as well, because this is only the case of D5 or D6. If I say if it is D7, there are like D8, like I have 8 electrons to fill. So whatever way I fill, it will be the same most of the time, or D9. Okay, so it will be the same. So this time I filled like singly, singly, but if what if I fill like this, 2 4 6 8 9 6 2 4 6 8 9. So it is essentially the same, right? So in this case we cannot say this is high spin, this is low spin. This is just, it was like an initial way to say, okay, this complex is high spin, this complex is low spin. I think nowadays we don't really care about that. Okay, so anyone else have any other doubts? Okay, so we'll move on to next question. Before that, I'll just give an overview of what complex is, or ligands and all. So this is a coordination compound. Fe stands for iron. Iron is the central metal atom, and this water is the ligand. So we can consider the central metal atom as a Lewis acid. So Lewis acid means what? It likes to accept electrons. Ligand can be considered as a Lewis base, which means which will donate electrons. So basically this coordination compound is like a donor acceptor kind of interaction, where the metal normally is a Lewis acid which will like to gain electrons, and the ligand is a Lewis base which will like to give electron. And if we can write something inside this square bracket, it means that whatever is inside, that is the complex. And this M, this is like a general formula. The M stands for the central metal atom, and there can be ligands. The ligands can be of different types. If it's a neutral ligand, we can call it like a, we can denote it like a L ligand. If it's a charged one, we can call it like an X ligand. And the number of ligands can also vary. and this can also have a charge like this, Fe3 plus. So from this we can get what is the oxidation state of the metal, how many ligands are there, and what is the coordination number. Coordination number is nothing, it is like how many ligand donor atoms are surrounding or directly connected to the metal atom. That is the coordination number. So in this case, there are six H2O molecule, and here oxygen is the donor. So there are six oxygen donors atoms directly connected to Fe. So here the coordination number will be 6, and the overall charge of the complex is 3 plus. But if I ask you to calculate the oxidation state of iron, how will we do it? So if since we don't know the oxidation state of iron, we can just keep it as X. And as you know, water is a neutral ligand, so there is no charge, 0, but the total charge is plus 3, right? So X is just plus 3. So iron is in plus 3 oxidation state in this complex, right? Mm. Mm. Yeah, so moving on to that, actually we have different kinds of ligands. We can actually divide the ligands based on the type of donor atom, or on how many number of donor atoms the ligand is giving to the metal. So in the type of donor atom, we can again divide into two classifications. It can be either neutral or ionic, and sometimes it can be both. Then another classification is sigma donor, pi donor, and pi acceptor. For example, let me take the example of NH3. So NH3 has a lone pair, as you all know, but this is a neutral molecule as well. So I can say that this is a neutral ligand. At the same time, it is connecting to the metal through this lone pair. So we can call it as a sigma donor ligand as well, like this. So NH3 at the NH3 at the same time is a neutral ligand as well as a sigma donor ligand. For pi donor ligand, I'll say Cl minus. So this is, I would say this is ionic, right? But this also has this pi electrons which can be donated to the d orbitals of the metal. So Cl minus is ionic as well as a pi donor ligand. Then this is pi acceptor. This is a very special case, and uh, based on this we have a separate branch of like inorganic chemistry called known as the organometallic chemistry. Here what happens is the metal is so rich in electrons, the metal will give back the electrons to the empty p orbital of the ligand. This normally happens with the ligands such as carbon monoxide. So carbon monoxide is also neutral, but it has an empty p orbital. So if the metal has so much electrons, if the metal is in so much if like more than like D8, D9, or if it has so much negative charge, it can give back to the empty p orbital of the carbon monoxide molecule. So these are the types of ligands, and there are also other kinds of ligands where same ligand can connect to two different kinds of donor atoms and all. That things I have not included here. And this is for example, these all are monodendrite ligand. Like it can, okay, this is a monodendrite ligand. This can connect only through the lone pair of nitrogen. So the donor atom here is nitrogen. But what about this molecule? This molecule has two nitrogens, right? So both can connect to metal atom. So the density, or this density of this molecule is 2, because two donors can attach to the central metal atom. So like that we have like bi, tri, tetra, poly, etc. Yeah. Mm. Mm. Um, yes, actually, if we look at this, the same example that I drew, NH2, NH2. So if I have a metal like this, the coordination number is 2 here. But if it was just one NH3, it is just 1. But also it depends on the number of ligands. If I have 2 NH3, then it's the same case. But the one thing about this density is that whenever the density increases, it's more difficult to break this bond. There is something called an effect called chelate effect, chelation or chelate effect. This is when, yeah, the ring. This is also a ring, right? So the whenever the density increases and there is like a this is like a one, two, three, four membered ring. If there is a five membered ring or six membered ring, which ring will have the highest stability and all those things. And whenever chelation increases, for example, I can show the same uh, example. So if I have to break or remove this ligand, I have to break at 2 points, right? I have to break at here and here, so it takes more energy. But if I have to remove this ligand, I just have to cut here. It's more easier. So in that case, whenever we have this chelating or multidentate ligands, they make the complex more stable. uh, yeah. So moving on to one question. What is the coordination number of Fe3 plus in the following complex K3 Fe C2O4 thrice? So here we have to look at this, what this K3 is. K3 is just an, yeah, or yeah, 1 second. Someone is joining, I think. Yes, sir. Yeah, it is stable. Yeah, but if we have to say there are reaction mechanisms. 1 second, people are joining. Okay. So I'm not saying that complexes are not stable, but in the transition metal chemistry or organic metal chemistry, that we can see a lot of reactions where the complexes are undergoing some like associative mechanism or by dissociative mechanism. Uh, like whenever another ligand comes in, that ligand can substitute one ligand or similar reactions. So in that case, like if there is a like in a bidentate or mono or tridentate or chelating ligands, when the incoming ligand comes, it's difficult to break that complex. And also there is something called reactivity of the complexes. The complexes can react, but depending on the stability, it's like the delta H values. Like if you look at that, whenever the metal is surrounded by the chelating ligands, it will be much more stable than the other ligands. I mean other complexes. Am I clear? Okay. So moving on to this question. Uh, so this is what related to whatever I discussed right now. Um, okay. So I don't know. My question is not visible. Okay, so the whatever is inside this sphere, that is the complex. Whatever is outside is just some ions to compensate the charge of the complex. So here each K will have how much charge? Plus one charge, right? So I don't know why I'm not able to see the cursor. 1 second. Okay. So uh, each K will have plus one charge. So we have 3K. So 3 into 1 is plus 3. So basically this is plus 3. Then this should be minus 3 for having an overall neutral system. So if I write the complex, it will be FeC2O4 3, 3 minus, right? So what will be the oxidation number of Fe here? Can anyone solve? Can put it in chat box as well. I'll give you one clue. C2O4 is the oxalate. Oxalate structure is C double bond O, O minus, O minus. So there are 2 minus for each oxalate group. So now please solve and put it in chat box. Okay, so anyone else wants to answer? Okay, so let's solve. Okay, so we need to find the oxidation number of Fe, so we'll just keep it as X. So X plus each carboxylate ion will give 2 minus, so 3 into minus 2 is equal to minus 3, because as I said the charge here is minus 3, this was plus 3, so it will be X minus 6 is equal to minus 3, so X is equal to minus 3 plus 6, which is equal to plus 3, right? So you are right, X is equal to the oxidation state of Fe here is plus 3, right? Okay, so this is the structure of the molecule that I have given, the same molecule here. So this is actually a bidentate ligand. See, this is uh, one ligand, and each ligand is giving 2 oxygen. So this is like example of a bidentate ligand. So what will be the coordination number for this? Can you please? Yes, 6. So 1, 2, 3, 4, 5, 6. So this the coordination number is 6. So option B is the right answer. Okay, now I have just kept 2 examples. This one we already solved. So for this one, I need to know what is the oxidation number of cobalt and what is the coordination number of cobalt. So please solve and put it in chat box. The oxidation number and the coordination number of this complex. Okay, plus 3 is the charge. Then what about the coordination number? Okay. Okay, maybe we'll solve together. Okay, so here also this is the coordination sphere, and these are just ions outside. So this is basically okay, this is corresponding to each chlorine will have -1, so 2 into -1 -2, this is -2, the whole complex will be +2, right? So cobalt NH3 5Cl 2 plus. So to find out the oxidation number, X is the one we don't know about of cobalt, and NH3 is a neutral molecule, so the oxidation number is 0. Yeah, anyone is talking? Okay. Then there is one chlorine, so it is plus -1, and it is equal to +2. So X minus 1 is equal to +2. X is equal to 2 plus 1 is +3, right? So whoever said the oxidation number of cobalt is +3, you are right, it is +3. So now we'll look at the coordination number. So we have NH3, 5, and NH3 we know it bonds through the lone pair, right? So there is only one donor atom, and we have 5 NH3, so 5. Then chlorine also bonds through this negative charge, so 5 plus 1, 6. 6 is the coordination number for this complex. So do you guys have any doubts regarding this? Okay, let me check the chat box as well. Okay, so we don't have any doubts, right? If you have any doubts, you can put it in the chat box as well. Okay. Okay, then I'll move on to the next one. So this is a simple trick that will help you while you are learning this transition metal chemistry or organic metal chemistry. Basically, you'll be dealing with the transition metals, which is this scandium from zinc. This scandium from the first row corresponds to the 3D elements. Then the second is 4D. The last one is 5D. So if we know these elements by heart, then you don't have to learn anything else in the transition metal chemistry or in the organometal chemistry. Trust me when I say that, like you might think that this is difficult to learn, but you can make some kind of mnemonics, or somehow you have to remember these ordering, at least the 3D, the first row. Then you can solve almost all the questions without remembering anything else. And what I have shown here, D1, D2, D3, all these things, these are the number of d electrons this metal will have when they are in their +2 oxidation state. So for example, if I ask what is the number of electrons in chromium 2 plus, we can just put up your finger and you can say scandium, titanium, vanadium, chromium. Okay, if chromium has +2, chromium in +2 state have 4 electron. And if someone asks you, okay, then what is the charge, what is the number of electrons in chromium in the neutral state? Then you already know that in +2 it has 4. So in neutral state means what? We have to add 2 more electrons, right? So 5, 6. So we have the D6. And there are many calculations where they ask where we have to remember or get the number of d electrons. So this will really help. So you just have to remember the order of the transition metals. The electrons you don't have to worry. You just open your hands and just start scandium, titanium, vanadium, chromium, manganese, Fe, cobalt, nickel, copper, and zinc. So by this trick, we can solve the next question. 1 second. So next time onwards, please come at 7 itself, because people are still joining and I have gone past 4 questions. Okay. Anyways, so we'll try to solve this question. Which of the following complexes will obey the 18 electron rule? So see, here we can't just look at the complexes and say that, okay, this one is an 18 electron complex. We can't say that. Even though initially people used to believe that all complexes had 18 electron rule, but there were many other examples where it was not the case. We could see 16 electrons, sometimes 14 electrons, all those things. But when it comes to the organometallics, like this, wherever this carbon monoxide, organometallics basically means organic plus metallic. So which means that there is a direct carbon to metal bond is happening. In those cases, it is expected to have 18 electron or sometimes 16 electron rule. But otherwise, we'll always have to work it out. So for chromium, we'll try first. First, we have to look at what is the kind of ligand we are dealing with. So yeah, it was believed that initially that the complexes are stable because they have this 18 electron rule. So you know that the argon or these noble gases are stable because they have completed their octet. So people used to believe that this is the same thing for complexes, because they found many complexes have 18 electron rule. But later they found that many complexes do not have 18 electrons. So that was just an absolute rule. But in some special cases, it is the rule. So it basically depends upon the molecular orbital interactions. Maybe I don't have the elaborate discussion on that right now, but maybe next class or some other time we can discuss. Yeah, yeah, that I will show now. So here, for example, we'll try for this one. So first, we will look at what kind of ligand we have. So I will now classify the ligands into two types, L type and X type. So L type just means that it is neutral, and X type means that it is anionic. And there is also sometimes LX type. In the same ligand, some part will be giving lone pair, some part will be having minus charge. For example, uh, this group. So it can donate from this part and this part also. So this is L and X type. So now another thing to notice is that each L will give 2 electron and X will give 1 electron. So this, if you remember, it will be very helpful for you. So for chromium CO6, CO, okay, one second. For chromium CO6, CO is a neutral ligand, so this L, which means it will give 2 electrons. So how many carbon monoxide do we have? 6. So 6 into 2, we have 12 electrons only from the ligands. Now we have to count how many electrons are given by the chromium. So we generally count the d electrons only. So for chromium, we have to see what is the oxidation state. So first we'll see, okay, you guys please help me in finding out the oxidation state of chromium in this compound. What is the oxidation state of chromium in this chromium CO6 compound? Anyone wants to put it in chat box? Yeah, -1. For uh, chromium, yeah, let's solve then. So it is X, we don't know the chromiums. So the carbon monoxide is having 0 because it is a neutral molecule, so 0, and we don't have any charge also. It is not, the charge is not written, right? Charge is also 0, which means that the chromium is in its neutral ground state, right? So now if we remember how many electrons chromium has in its +2 state. So I know scandium, titanium, vanadium, chromium. Here, see this one, yeah, 4 electrons in its +2 state. Now but we need it in the 0 state, which means that we have to add 2 more electrons. So the number of 6 electrons, right? So the chromium will have 6 electrons. So the total number of electrons here is what? 6 plus 12, 18. So this complex definitely follows the 18 electron rule. Okay, now we will solve the next one. Okay, so this one, the eta5C5H5, this is a special kind of molecule. It is called a cyclopentadiene. This is a cyclopentadiene with 2 double bonds and 1 minus charge. So this is like a L2X kind of molecule. One second. People are still joining. Okay. Okay, so this is like an L2X kind of molecule because this the uh, this molecule can bond with the metal from this pi bond, pi electrons, and through this negative charge. So it is like an L2X. So each L will give how many electrons? 2. So 2 into 2 plus 1. So it will be 5 electrons, right? Um, and actually sometimes you can see this molecule uh, in another way, like this. bonded to Fe, something like that. And there is a very famous molecule like which is called ferrocene, where the Fe is like sandwiched between these two cyclopentadiene rings. So, and this N eta 5 means that five carbons are involved here. One, two, three, four, five. So when we count the coordination number, we have to count this five. 1, 2, 3, 4, 5. And there is another way also it can interact only from through the double bonds. It will be like then 1, 2, 3, eta 3, C5, H5. Sometimes this C5H5 is just called CP, cyclopentadiene. So it can be eta 3 CP or eta 5 CP, even eta 1 CP is also possible, where it coordinates only through the negative charge. So this CP you generally see in the organometallic chemistry, um, but let us, okay, let us count the rest of the electrons. So here this is hapticity, this eta is called hapticity. I mean the how many number of carbons or the atoms are linked to the metal. So the hapticity, this is in hapticity 5, which means it is in L2X state. So each L will have 2 electrons. Yeah. Yes, yes. After which part? Okay, okay, okay. Maybe I'll just take one. Okay. So CP is cyclopentadiene, just a 5-membered ring. Normal CP is actually, you know, it is like this, but when the ones that we when that we encounter in complexes is charged, like there are two hydrogens here, one hydrogen is just removed, so it is a charged species. So it is like an L2X kind of thing, because this the pi electrons can also contribute to the metal and along with this negative charge. So 1, 2 both are L and this is X. So 1 L will give 2 electrons. So 2 into 2 plus 1. So X will give 1 electron. So each CP will give 5 electrons. But this is in the case of eta 5. Eta is called hapticity. This means how many atoms are connected to the metal. So this is a hapticity 5 state where each, you know, pi bond and this negative charge is interacting with the metal. Then there is another mode where only this part is interacting with the metal. So here 1, 2, 3, yeah. So this is the hapticity 3 part. Then we have hapticity 1 also, because this one through this. And it is actually called as CP instead of C5H5. You'll just generally see CP, and it will be either eta 5 CP or eta 3 CP or eta 1 CP and so on. Okay, so now we will calculate how many electrons are there. So as we saw here, this eta 5 CP will give how many electrons? 5 electrons. So 5 plus ions we don't know. Carbon monoxide will give 2 electrons, and there are, because it is a neutral ligand, so and there are 2 carbon monoxide, so 2 into 2. plus Cl. Cl is a X type of ligand, so it will give 1 electron. So just from the ligands we have 5 plus 4 plus 1, 10 electrons. Now we will look at what is the oxidation state of iron here. So uh, please solve for the oxidation state of iron and put it in chat box. What is the oxidation state of iron in this second complex? Yes. Yeah, normally when if it is like 5, they'll just give here. Like as such, we don't know if it is hapticity 5, 3 or no. But some they most probably most of the time, I mean not most of the time, all the time if they are giving the complex, they will write if it is hapticity 5 or hapticity 3 or hapticity 1. So from that we can calculate how many electrons are there. I mean how many electrons are contributing. Okay. So have you guys solved for the oxidation state of iron? Chat box. Anyone wants to answer in chat box? What is the oxidation state of iron in the second complex? Okay. Okay, I'll give you some time. This is a simple question, right? People can, you should try. Okay, the Cp will give 1 minus charge. Please note that it is an L2X kind of molecule, so it will be giving 1 minus charge. Okay. Okay, then we'll discuss. Okay. So I am asking for the oxidation state, so not the number of d electrons. So we'll just find out here. So we know that for Cp we have 1 minus charge, so minus 1, plus for Fe we don't know, so X. For carbon monoxide is 0, so 0 into 2 plus minus 1 from the chlorine, and it is equal to 0. So basically it is X minus 2 is equal to 0, so X is plus 2. You guys got it, or do you have any doubts in calculating the oxidation state? Okay, okay. So from this previous diagram, we know that Fe in plus 2 state has how many electrons? T6. So we just have to add here 10 plus 6, which is 16 electrons. So it is not an 18 electron complex, it only has 16 electrons. So now we will solve for the next one, nickel Et2 carbon monoxide twice. So let me just say what is Et. Et is ethylene, you know, right? CH, CH, CH. So from this double bond, it can give one pair of electrons. So this is a neutral molecule. So it's just L-type molecule, right? So what is the oxidation state of nickel in this complex? Nickel in this complex. Please write it in chat box. What is the oxidation state of nickel in this complex? Yeah, good. So you are right. Let's discuss anyways. Okay. The complex is nickel Et2CO2. So X for nickel, we don't know, and Et, as I said, is a like a neutral ligand, so 2 into 0 plus carbon monoxide is also neutral, so 2 into 0 is equal to 0 because this is overall neutral, so X is equal to 0. So nickel is in its normal, neutral state. So now we will look at the diagram. So nickel is this, at +2 state it has D8. So what will be the number of electrons in in 0 state? Anyone wants to answer? Nickel 0. How many d electrons will it be there? Nickel 2 plus is D8. So nickel 0, D? No. See, electrons we have to add, right? It's like, when will we get 2 plus? This is, okay, let me discuss that. This is nickel 0. We have, okay, let's say 10 electrons. Now, when will I get 2 plus? When I remove 2 electron, right? Then I'll get nickel 2 plus. Then it is 8 electron. So if I already have nickel 2 plus, it is 8 electron, how will I go to nickel 0? You just have to add 2 electron, right? Because here you are removing electron, here you are adding electron. So basically we have D10. Nickel 0 is D10. Is it clear? Okay. So the number of electrons here is 10 for nickel plus Et. Each Et is L-type ligand, and each L will have 2 electrons, and there are two ETs also, so 2 into 2 plus each carbon monoxide will give 2 electrons, so 2 into 2, so 10 plus 4 plus 4. So this is an 18 electron compound, right? Yeah. Okay, now you guys have to solve the last one. How many electrons are there in the copper H2O6 plus? This is the most easiest example in this set. Please write it in the chat box. I just want to know what is the number of electrons in this complex, cobalt H2O6 plus. Total number of electrons in this complex. Okay, the oxidation number of copper is 2 plus, right? But what is the total number of electrons in this complex? Okay, maybe I can give you a hint, because this one. So copper, this is copper. Copper in its +2 state have how many electrons? Yeah, 9 electrons. And now you just have to add the number of electrons provided by each water atom. So please write it in the chat box. How many electrons do we have? Total number of electrons. Maybe will discuss again. So copper, as we discussed, is in +2 state. I'll just show. X is for copper and water is neutral, so 0 into 6 is equal to +2, because the overall charge is +2. So X is +2, which means copper 2 plus. And from here we can see copper in 2 plus state has D9 electrons, that is number of electrons is 9, right? Yeah. So 9 plus each water will give, water is a neutral ligand, L type ligand, so each water will give how many electrons? 2. Yeah, so 2 into 6 because there are 6 water. Uh, and here it is equal to 9 plus 12, which is equal to 21. But here actually you have to, mm, yeah, this is fine. Yeah. Okay, so anyone have any doubts here? Yes, yes. Okay. Okay, now these were all the calculations and all. So now we will see some applications of this metals or the inorganic chemistry in biological systems. So as you know, like there are many metals that we are closely related to. I mean, in the biological processes, and this is a direct question. And all these questions are part of the assignment zero that was given for the same course, but last year. Uh, so this directly asks which biologically active species control important cellular processes such as oxidation or reduction, hydrolysis, methyl group transfer, etc. The options are metalloproteins, free proteins, and free methyl ions. So now we have to look at what are the processes they have talked about: oxidation, reduction, hydrolysis, and all those things. So intuitively you should think about who are the like who will undergo all these reactions. We have heard about metals undergoing oxidation, reduction, etc. But we also know that the free metal ions cannot remain in body without any associations, because free metal ions are like, they don't just Fe2 plus, if I say, they don't like to stay alone. They'll always complex with some water or some other ligand to form a complex, right? So it cannot be free metal ions. And free proteins are just a combination of amino acids, some organic molecules. They don't really undergo oxidation reduction as good as the metals. So it should be the combination of free proteins as well as metal ions. So the answer here is metalloproteins, and this is a like a figure image of hemoglobin, and all these ribbon kind of things are the proteins, and this green kind of thing is the major is a heme containing moiety, which is the heme, which has the iron inside it, and iron actually helps the hemoglobin, as we know, to transfer oxygen in blood, right? um, so do you have any doubts here? It's a straightforward question. Yeah. So here another question is, what is the oxidation state of iron in hemoglobin and myoglobin respectively? This is also a very straightforward question, and for uh, like frankly, for bioinorganic chemistry, bioinorganic chemistry is the part of inorganic chemistry where we deal with metals and other metallic substances in relation with the biological things. So we'll be talking about metalloproteins, metalloenzymes, like hemoglobin, all those things. So this is also a straightforward question. What is the oxidation state of hemoglobin and of iron in hemoglobin and myoglobin? And the answer is this: Fe2 plus, no, not this one, Fe2 plus and Fe2 plus. Both have same state of iron. So I'll just give you an overview about what this myoglobin and hemoglobin are. So myoglobin and hemoglobin are both globular kind of proteins. So from this word globin itself, you'll understand that it is like some globe like structure. Globe means round or circular or spherical. So basically both are globular kind of proteins. They have like a a spherical appearance. And hemoglobin is the compound that gives our blood the red color, and it is the one which carries oxygen. And myoglobin carries oxygen in the muscle tissues. This is the hemoglobin carries oxygen in the blood. This one carries oxygen in the muscle tissue. It is specifically for muscle tissue. And this is the structure. Both myoglobin and hemoglobin have the heme moiety, which is here. It is like a organic system. It is like a conjugated system, and in the middle of that we'll have iron. So both of them have this moiety, but one main difference is that myoglobin has only one chain. This is the only chain. but hemoglobin is a tetramer. Like there are four chains, 1, 2, 3, 4. Like 1, 2, 3, 4, and it is a heterotetramer. Like there are two kinds. This orange one is one kind, this blue one is another kind. But myoglobin is just one kind, and it's only one monomer. That's called a monomer, and hemoglobin is a heterotetramer. And just these are just the some other information, how many amino acids are there in myoglobin and hemoglobin, all those things. And these are not directly related to the chemistry. This is just an overview. But I would like to go to this part where how oxygen is connected to the hemoglobin, and how exactly the inorganic chemistry comes into play here, and how we can understand that. So this is the heme part, the organic part that I was talking about. This pink one is the Fe2 plus, and normally when there is no oxygen, and that is called the deoxy form, where then there is no oxygen, and during that time, normally this the organic compound is like a very planar kind of thing, but when there is iron is there, it is like a dome shaped, like here. See, this is not planar, it is like a dome shaped structure. And from here we can see something called a histidine. Histidine is an amino acid, and it is not terminating here. From here there is like a huge branch of protein chain, like how you see here, like from histidine, like this much big branches coming out. But just to show representatively, I have just cut off from this part. So basically, when there is no oxygen, iron is the iron containing heme is in a non-planar domed shape, and there is a histidine here that is called the proximal histidine. Proximal means it is closer. Then there is another one called a distal histidine. Distal means it is far away. So in this state, the ion is in paramagnetic in nature. So we were talking about the high spin, low spin, those things, right? So in Fe2 plus state, we have these 6 electrons, right? So paramagnetic, then how will it be paramagnetic? It means that it is in high spin state. See the number of, these are not, uh, there are a lot of unpaired electrons, which means that it is paramagnetic. Paramagnetic means whenever there is an unpaired electron, that is called paramagnetic. Diamagnetic means whenever there is all electrons are paired, there should not be any unpaired electron. So even though this is Fe2 plus and it is paramagnetic in nature, in the oxy form, that is when the oxygen comes, then this Fe2 plus remains the same oxidation state, the same Fe2 plus, but it becomes diamagnetic, which means that it changes its spin state. It changes to a low spin state. 1, 2, 3, 4, 5, 6. It is low spin state. So it is something actually like some kind of miracle. Without changing the oxidation state, we are having a different electronic configuration, and due to which something else happens. See, whenever there is like electrons occupying this E2G group, E2G orbitals are the orbitals that is like a bit far from the nucleus, so it is like much more diffuse compared to T2G. So it means that whenever the electrons are occupying in this EG, then there is like more like to reduce the repulsion, it goes like more like out of the, it becomes more diffuse, which makes the whole atom a bit bigger. This Fe2 plus iron is a bit bigger. That is why it is actually out of this plane, 40 picometer out of the plane, the domed shape. But when the Fe2 plus becomes low spin, that is diamagnetic, the T2G6 EG0, that in that case there is no electron in this EG state, so the electrons are all kind of compact, and the size of the Fe2 plus ion reduces. Now it can become in plane. See, now it can become in plane. So basically, without the change of uh, oxidation state, the size of the cation is changing, and with it the whole shape of the protein is changing. And now what happens is, this happens when this oxygen is coming and attached with this Fe. The oxygen is coming and attached with Fe. In that case, this reorganization of electronic configuration occurs and Fe becomes in plane. Now another thing happens is what? This proximal histidine was also like this, right? So when the oxygen is coming here, this Fe is also coming down, and this proximal histidine is also coming down. So with it, the whole protein is coming down. And if you see here, all these are connected. So if one part is coming down, the other part is also like coming down. So basically, if one oxygen is attached, then it makes the attaching of other oxygens more easy. This is called a cooperative effect. See, one it's something called cooperative effect. Like one, just by attaching one oxygen, the other um, protein parts are also able to attach to or bind to oxygen more easily. So this effect is not seen in myoglobin, because myoglobin only has one protein chain. It cannot attach to any other. It is not attached to any other chain. So there is no point in, there is no cooperative effect. Um, then there is something called a distal histidine, which is not shown here. And I think you have all heard about carbon monoxide poisoning. And we have heard that when we inhale so much of carbon monoxide, we will die, because the oxygen, we will be dying of carbon monoxide poisoning, right? But how actually, the same heme moiety, whenever it is decomposing in our body, it is also producing carbon monoxide. And by part of many reactions, our body is producing carbon monoxide. But why we are not getting any carbon monoxide poisoning from our body? For that, for that, the distal histidine comes into picture. Okay, distal histidine is shown here, right? So distal histidine is arranged in such a way that the carbon monoxide cannot come and attach in the straight way. So carbon monoxide, when it comes normally, it will attach like this straight to the hemoiety. But because of this histidine, it cannot come like this. It is a bit bent, like not straight, something like this or something. Because histidine is this, histidine is a very bulky part. So because of that, this carbon monoxide cannot directly, like in a straight line, cannot connect to Fe. Because of that, it is a bit bent. When it is bent, then we can see that the stability of this bond is not that much. Then the oxygen can easily come and break this bond and come and attach to Fe, so we don't get the carbon monoxide poisoning. But if we are in, like when we inhale so much of carbon monoxide, then the concentration of carbon monoxide increases, and then oxygen cannot do anything. But if it is in the like lower level, then our body can manage up to a level. Okay, do you guys have any doubts in this session? Hmm. Hmm. Yes, oxyform, yes. Yeah. So when it is without oxygen, it is called the deoxyhemoglobin, and with the oxygen, it is called the oxyhemoglobin or the oxyform. So I know that I have given so much of information, but I just wanted to like connect the inorganic or the metals with the real thing that is happening inside our body. And there are many techniques also to study how we are like how we can manage, how we have studied this, or how like the Raman spectroscopy. There are many spectroscopic techniques available for the inorganic compounds as well, to understand our biological how the biological reactions are going on and all. And I'm sure that you have seen during COVID and all, there were a lot of pulse oximeter things. This is also based on the hemoglobin. Like the oxyhemoglobin absorbs light at a different wavelength than the deoxyhemoglobin, and by that difference, the pulse oximeter like calculates, okay, how much is difference, and from that it just calculates how much oxygen is there in our body. Okay, so any doubts in this? Okay, let me just check chat box as well. Yeah, yeah. Let me see. One second. This one. We have not counted because it is outside the sphere, right? So see now, another thing I have to clarify here is that what actually is a complex. Like if I dissolve this compound in say water or something, and if I test for some halogen for chlorine reagent, like if I test with maybe say AgBr or something, then I'll get AgCl, like precipitate. But only this Cl will react, not this Cl. So if it's react, it is not part of the coordination compound. Like if we can just remove it part by part, it is not the coordination compounds. That's why it is outside, and that's why we just treat it like a counter anion. This is plus 2, this is minus 2, just for keeping charge. For instead of Cl2, you can just keep maybe Br2 also, doesn't matter. Okay. uh, okay, so okay, this is also a direct question. Transference control the level of free dash in biological fluids. So from the, in biology or biology related questions, you always have to look at what they're asking. From the question itself, sometimes we can answer. So from this word ferrin, you have to immediately think of ferrum, which is iron, right? So it is just this. Transference control the level of free iron in biological fluids. This transferrin is kind of a protein which stores up extra iron in the liver, and whenever we need iron, we can just it just takes from the liver and just utilize it. uh, yeah. Okay, 7, slide number 7. Like not slide number 7, like 9. Okay, let me just, I'll share again, one second. Okay, now can you see question number 7? Okay, so I was just saying that like whenever this biology related questions come, you just have to look at the keywords. I don't know, my cursor is missing now. One second. I was just saying that whenever the biology related questions comes, you just have to look at the keywords. So the keyword here is transferrin, ferrin. So you have to look at this word ferrin. So from the options, okay, there is iron, cobalt, manganese, and zinc. So from this, immediately you have to think, okay, Fe means stands for ferrum. So most probably it should be something related to Fe, and it is in fact related to Fe. The transferrin is a kind of protein that stores the extra Fe in the liver, and whenever the body needs it, it just takes it from the liver and utilize it. Am I clear? Okay. So this is a very simple question. You guys should answer it. So which one will be paramagnetic? Paramagnetic is the number of, like if there is any unpaired electron, it is called a paramagnetic. And for those of you don't know the atomic number, I have given the atomic number also. For aluminum it is 13. For magnesium it is 12. So please write in the chat box which one will be paramagnetic. Okay. Okay. Okay, so we'll just uh, discuss. So from the off-bow principle and all, we already know. 1 second. Okay. So from the off-bow principle, no, any of the orbitals, but you just need to look for unpaired electrons. There should be unpaired electrons. If there is at least one unpaired electron, that is called a paramagnetic substance. If there is no unpaired electron, that is diamond. Yes, the answer is aluminum, because I'm not able to write. I don't know why. Something happened maybe. Uh, yeah. So the aluminum is the right answer, because for aluminum we can just write the electronic configuration: 1s2, 2s2, 2p6. This is 10 electron. Then 3s2, 3p1. Yeah. So there is one unpaired electron. Therefore, aluminum is paramagnetic. For magnesium, it is just 1s2, 2s2, 2p6, 10, then 3s2. That's it. So now I just want to ask one question. In which group does aluminum belong to? Okay, at least say which block, S, P, D. Which block does aluminum belong to? Please write it in chat box. Yeah, yeah, right. So aluminum belongs to P block. And what about magnesium? Yes, right. So magnesium uh, belongs to S block. So that's the end of my questions. And if you have any doubts, you can ask now. And those of you who have joined later, like if you want to see any questions, we can discuss. Yeah. Isoelectronics means the same number of electrons. So, for example, I can say, okay, so, 1 second. Let's say aluminium. Aluminium in zero state, we just saw that it is atomic number is 13. So number of electron is also 13 in its ground state. So, and Mg in its ground state is 12 electron, right? So if I write Al plus, what is the number of electrons in Al plus? 12. So I can say that magnesium and aluminium plus are isoelectronic species, the same number of electrons. That's it. For the compounds also we can do the same thing. For example, like how we calculated the the 18 electron rule. Here we saw that the chromium CO6 is 18 electron, and then the nickel Et2, this one is also 18 electron. So in this case we can say that CrCO6 and this complex are isoelectronic in nature, because both of them have same number of electrons. So it just depends, like in for transition metals and organometallics you can just add like this, but if you're dealing with some say water or something, you can just count up the valence electrons. Yeah. Do you have any more doubts? Anyways, I'll just go from first slide to the last slide. If any of you have any doubts, or those of you have joined later, you can just ask me to repeat any questions. Or so in this one we just looked at what is the rules of nomenclature for elements of atomic number greater than 100. uh, then then here we were looking at the increasing order of energy of orbitals and how we will write electronic configuration on the basis of Aufbau principle, and how Aufbau principle is derived from this n plus L rule. Then some other rules, which is Hund's rule of maximum multiplicity and Pauli's exclusion principle, which helps us in writing the electronic configuration. Then what is a complex, and what is the nature of the ligands in the central metal atom. The central metal atom generally is a Lewis acid which likes to accept electron, and ligands is normally a Lewis base which likes to donate electrons. And whatever we write inside the square bracket is a uh, it's a complex, and we can this is a metal and these are the ligands, and this is the overall charge on the complex. And we saw that there are different types of ligands. It can be on the basis of donor atom, or how many number of donor atoms are participating in the coordination, or the type, the neutral or ionic, or through what bonding. Sigma, it is a sigma donor, or is it a pi donor, or is it a pi acceptor kind of ligands. Yeah. Hmm. Hmm. Uh, Generally, like by just looking at the molecule or the ligands, we will come to know. For example, for NH3, NH3 has only the lone pair, so it is the sigma donor. And like the chlorine minus, the minus is in the p orbital, right? So it is coming from the pi. And in carbon monoxide, if you look into the molecular orbital diagram of carbon monoxide, you will see that it has a empty p orbital, so it is a pi acceptor. So from it is not like if you know the molecular orbital diagram, or something, even if you don't know, like if you know which all orbitals are taking part, if you know the valence orbitals, then you will be able to know. And for some, the uh, like the normal kinds of ligands that we encounter, after some practice we'll be like knowing it. So the normal questions we'll be able to answer. Yeah. Okay, then we looked at the coordination number of iron in this complex. How do we calculate the oxidation state? How do we calculate the coordination number, etc. Then we solved some examples. Then this is a cool way to learn, remember how many electrons are there in the transition elements. And if you at least learn the first row, then you will be able to solve most of the questions. And rarely people ask the third row and all. In second row, sometimes they ask rhodium and palladium related compounds, because when you go much forward in chemistry, like during your MSc or something, you will have to learn the catalyst cycle and all. Then you'll have to look at the oxidation state of rhodium, palladium and all. During that time, maybe you can learn that. But for undergraduate, I would say that the 3D, just learning the 3D elements in the right order helps. Then we solved the example of which like counting the electrons in a complex. Then um, then we dealt with some straightforward questions related to the biology, and biology, the metals in biology, how metalloproteins are doing the cellular processes like oxidation, reduction, hydrolysis, etc. And we just had an overlook of overview of myoglobin and hemoglobin and the oxidation states, and how this iron is changing its property when the oxygen is coming and oxygen is not there, and how this change in property is helping the hemoglobin to attach more oxygen, and all. Yeah. No, I for this course you don't have to learn. This is just like an introductory part I have just given to just to give an outlook. So you don't have to learn these structures. For these for these complexes also, you don't have to remember the, the number of carbon monoxide, all those things. You just have to remember, if you get a complex, how to calculate the oxidation state, how many electrons are there in that metal, and what kind of ligand is this, how many electrons this ligand will give. That is the only thing that you have to study. There is nothing else to actually remember in organic metallic chemistry or transition metal chemistry. That's it. And yeah, and your general chemistry knowledge, like Cl will give, Cl is in -1 stage, it means it will give 1 electron. That kind of general knowledge is fine. If you learn this, if you learn this order of 3D, then nothing else will be difficult. Like everything else will be like cakewalk then. Then yeah, then we just dealt with another straightforward question of how the transference control the level of free ion in biological fluids. Then we just solved which one will be paramagnetic. So if you guys have any doubts, or do you want me to repeat any question or anything, any other questions not related to the slides is also fine. Okay, let me see in the chat box if anyone is interested. Okay, so does anyone have any other doubts? Please put it in chat box if you have any doubts related to whatever I took right now, or the course in general. Hmm. Yes, yes. That actually comes in the organometallic, I think, and there is a specific formula for it. So I don't know if sir has taken that in the classes. I think in the week one he has not covered it, I think. So maybe next class I will show. I don't have the formula right now. Hmm. Any other doubts? Okay. So if we don't have any doubts, we can leave. So I'll be taking another session next Tuesday, the same time, 7 to 9. So please join at 7. If you are joining in between, you won't you won't see most of the questions. You want to understand if you are coming in between. So next Tuesday, 7 to 9, or if you want to join other session, there is a session, I think, on Sundays, 3 to 5, I think. I'm not sure about the timing. So any session you can join, just fine. Okay. So yeah. So yeah, we can leave, and we'll see you next class. Okay. Thank you. Thank you all. Thank you. Bye.